All right, so today we're going to work on the second half of section 4.2b. Our focus today will be looking at graphs of log equations. So again, it's going to be important that we remember what an exponential graph looks like so that we can compare it to what our log graphs look like. So these first two questions are just review from yesterday. Let's go ahead and graph y equals 3 to the x power. Make your table. And we'll just go from -2 to +2. What is 3 to the -2? It's going to be 1/9. Remember that negative exponent makes it flip over. 3 to the -1, 1/3, anything to the 0. 1, 3 to the first power, and 3 squared. All right, so plotting those points. We get that nice smooth exponential curve. And what do you remember about the asymptote? Where would our asymptote be? At y equals 0? All right. So that tells me my domain is going to be, everything above 0. Sorry. Domain everything, -infinity to infinity. Range, everything above 0. Okay. What happens when our base is a fraction like 1/2? What shape did our graph have? So it looks like the first graph we just did, except it's reflected over the y-axis. So it should be more of an exponential decay curve. All right. (1/2) to a -2 power. The negative is going to cause that 1/2 to flip and become a 2. And then we square it and we get 4. 1/2 to a -1. Okay. Anything to the 0 we said was 1. 1/2 to the first, and 1/2 squared. Okay, so -2 we're up at 4. -1 we're at 2. 0 we're at 1. Then down to a 1/2 and down to a 1/4. So again, it's that exponential decay shape. Do we still have an asymptote at 0? So y equals 0 is our horizontal asymptote. Domain is everything again, but range is everything above 0. So when we convert these and think of them as log graphs instead, we want to think of it in its exponential form. If you're asked to graph a log, you really should think of it in its exponential form. You know how to graph exponential graphs, right? So our hint is to switch it to exponential form. So if I'm asking you to graph g of x equals log base 3 of x, g of x is like our y, right? So y equals log base 3 of x. What would that be in its exponential form? How do we rewrite that exponentially? We start with our base, 3 to the y should get us back to x. All right. Now, here's the easy way to graph these. Pick your y's. We're used to making a table where we always pick our x's, right? But it's going to be much more difficult to pick an x value and then to try to figure out what power that needs to be. It's going to be much easier to pick the y values and work to find your x's. And you can do that. So for our y values, we're just going to go from -2 to 2 again. You don't need to make this overly complicated. All right, so if we take 3 to a -2 power, what do we get? Okay. If we take 3 to a -1 power, we get 1/3. 3 to the 0, 3 to the first power, and 3 squared. What do you notice about those points compared to the first example we did today? They're just flipped, right? In our first graph, our x's were the -2 to 2 numbers, and our y values were the 1/9 to 9s. Here we've got that reversed. Those mean we have inverse functions, right? If our x and y's flip-flop, we have inverse functions. So 3 to the y equals x is the inverse of 3 to the x equaling y. All right, let's plot our points. So we're over 1/9 and down 2. We're over 1/3 and down 1. 1, 0, 3, 1, and 9, 2. So instead of with our exponential graph here having a horizontal asymptote at 0, when we do the inverse, we now have a vertical asymptote at 0. So we are coming up along the y-axis and curving off to the right. So my asymptote would have what equation? Yep, so this time x equals 0 will be the vertical asymptote. And how about domain? Domain is restricted now, right? We have a vertical asymptote. There's nothing on my graph that's going to go past that vertical line. So my domain is everything above 0. But what about the range? Yes, there's no restriction on range. So -infinity to infinity. Compare all of those answers to the first question we did. Everything is just flip-flopped, right? Your x's now are your y's are now your x's. All right, so let's look at this next example. G of x equals log base 1/2 of x. If we write this exponentially, we're saying 1/2 to the y value should get us to x. Again, that is just the inverse of what we did right above it. Okay? So we're going to pick our y values again. One-half to a -2 power gets us a 4. 1/2 to a -1 power is 2. 1/2 to the 0 power is 1. 1/2 to the first is 1/2, and 1/2 squared is 1/4. Plotting those points. So our graph still has a vertical asymptote at x equals 0. But this time our graph is coming down along that y-axis and curving off to the right. Compare it to the graph we had right above. If I reflect this one over y equals x, this branch here is going to flip down and be this branch. And this flattened out part is going to come up and flatten out along there, which is the shape that we're seeing down here. Does that make sense? So everything is just the inverse. All right. So f of x equals 3 to the x and g of x equals log base 3 of x are inverses, just reflections over the y equals x diagonal line. When our base was bigger than 1, we get that shape. When we had a base like a 1/2, something between 0 and 1, we're always going to get that shape. All right, so transforming them. We can transform log graphs the same way we've been doing every other function. Let me go through each of these and then I'll pause the video and let you guys write stuff down. For the first one, log base b of x minus h plus k. Your h and k are just your normal left, right, up, down movements. If there's a negative in front of your log statement, it's going to affect your y values. It's a reflection over the x-axis. And if we put the negative inside with x, it's a reflection over the y-axis. It's changing our x values. All right, so I'm just going to pause the video for a second, let you write that down. All right, so we are going to transform graphs. And if you look at all of the examples we have left in our packet, it's all log base 3 of something. Okay, so we're going to start with our parent function, y equals log base 3 of x, which means if we do our little circle and write it exponentially, 3 to the y equals x. And we said when we're graphing logs, it's easier to pick our y values. So 3 to the negative 2 power, it's going to square it and flip it, so 1/9. 3 to a negative 1 just flips it, 1/3. Anything to the 0 is 1. Anything to the first power is itself. And then 3 squared would get us a 9. So I'm going to give you guys a minute. Just pause the recording. I want you to graph those parent function points on the rest of our grids. All right, because we're going to just use that same function for all of them. So all of your graphs should now have the parent function points plotted. To the right 1/9 down 2, to the right 1/3 down 1, 1 0, 3 1, and 9 2. So what kind of transformation are we doing on this first one? We are shifting right 1. If we move all of our points just 1 to the right, what else moves that we don't actually have drawn yet? The asymptote. So when we looked at exponential graphs, that horizontal asymptote moved when we had an up and down shift. When we look at vertical asymptotes, they're going to move anytime there's a left and right shift. So we are going to have a vertical asymptote that shifted right 1. So our graph should be coming up along that line and curving over to the right. So what's the equation for the asymptote? X equals 1. It's our vertical asymptote. Our domain, okay, everything past 1. And range is everything, negative infinity to infinity. Okay. For our next one, now which way are we shifting? Down one? Will a down one affect our asymptote at all? No. Moving all of our points just down one. We still are coming up along that y-axis. So we have a vertical asymptote at x equals 0. Our domain is tied to that asymptote, right? It has to be to the right of it, so everything above 0. And we have no restrictions on our range. Okay? For the next one, notice that our next two graphs both have negatives in them, but the position of the negative matters. So in the first one, that negative means we're reflecting over a negative in front is going to affect my y values. They're all going to be opposite of what they were before, which means I reflected over x. So let's take all of our points and just flip them over the x-axis. So now we have a graph that's coming down along that y-axis and curving off to the right. We have a vertical asymptote still at x equals 0. Our domain is still everything above 0, and our range is everything. If the negative is inside with x, it's now affecting my x coordinate, which means I'm flipping this over the y-axis. So instead of the point 9,2, I'm going to have the point negative 9,2. Instead of the point 3,1, I'm going to have negative 3,1. Instead of 1,0, I'm going to have negative 1,0. And my other 2 points also reflect over the y-axis. So this time we're coming up along the y-axis and curving to the left. We still have that vertical asymptote at x equals 0. But what can you tell me about domain? Now 0 is the highest, right? We can't go past it. So domain would be everything from negative infinity up to almost 0. Range is still everything. All right, so I'm going to pause the recording. I'd like you guys to talk to your partners about the transformations that you see in these next two graphs, and then go ahead and plot them. We should have the parent function already plotted. If you don't, use those same points that we've had for our 3 to the y equals x equation. So for this first one, what does this 2 in front do? All right, vertical stretch of 2. So what does that affect? Which coordinates? The y's. So our y's are just getting doubled. They're going to be twice as high as they were. So this point over here at 9,2 is going to move to 9,4. Our point at 3,1 is going to move to 3,2. Doubling 0 is still 0. What if we double negative 1? We're at negative 2. And if we double negative 2, we're at negative 4. So it's just stretching out that gradual shift towards the y-axis. Did it affect the vertical asymptote? No. So we still have a vertical asymptote at 0. Our domain would still be everything above 0, and arrange everything. Okay, for this last graph, the +1 is in front, and some books always write log equations that way. We're used to seeing that +1 on the end, right? It means the same thing. So what kind of transformation are we looking at? Up 1. We're going to shift everything up 1. It did not affect asymptote, domain, and range, so all of this applies to that one as well. Can we predict the domain? We know range is everything. Can we predict the domain just by looking at the equation without actually seeing a graph? What causes the domain to change? What kind of transformations? Anything left or right? Okay, so in this first example here, it says to find the domain without graphing. And remember, yesterday when we talked about log base e of x, I said there was another way we could write that. Does this look familiar? That ln, it's referred to as natural log. E is called the natural base. So natural log just means base e. E is what number? 2.718. So it's going to be very similar to our log base 3 graphs, right? They would just be decimals. So you still should be able to picture it just like the ones we've been graphing. Which way are we moving this? We're going right 3. So if we picture shifting everything 3 to the right, now our vertical asymptote is there. And our graph is coming up along it. Yes? So we should be able to list the domain without actually graphing it, just visualizing it. In this case, our domain would be everything above 3. Okay. For question 2, which way have we shifted it? Left 5 and up 2. Does the up 2 matter? Doesn't affect my domain. It's going to it's going to move my graph up 2 spaces, but it's not going to affect where it levels off. The left 5 is. So if everything shifts to the left 5, we now have a vertical asymptote at x equals -5, which means that our domain would be everything from -5, everything above -5. Okay, so we should be able to make those predictions without actually having to graph it. Questions on graphing logs. What's the key step in graphing a log equation? To do what? Write it in its exponential form. And then when you make your table of values, you're going to pick the y's instead of the x's. All right. So you're working on page 466, 53 to 62, 65 and 66, 69 to 72, and 75 and 76.